So let's start the third talk. This third talk is Professor Zhouping is come from the Hong Kong University, Chinese University of Hong Kong. Professor is a big professor before he worked in Klein Institute. Now he's the director of this Institute of Mathematical Science, CUHK. This morning's talk, we will talk about on smooth transonic flow under the mixed type equations. Let's welcome.
Thank you. And Professor Wang is my friend, so but he made two big mistakes in his introduction. One is I'm not big, okay, very short. Yeah. Second, I'm not a director, okay. The director of the Yuan. It's dangerous, okay, to say I'm a director. Anyway, so I'm from Hong Kong, and we do have a small institute in there. So welcome you guys to stop by if you want. We have our institute is much small compared with this size, but it's quiet, and welcome you guys stop to give us talks and do collaboration or communications. Yeah. So thanks Delpha for the very nice talk, just in front of previous talk, and so we are discussing about similar things, but I'm more on fluids part, so my talk will concentrate on transonic flows. And I try to give from this different perspective about the similar problem, okay? And some of the work I presented here is a joint work with my collaborators, Chunpeng Wang. He now is a professor in Engineering University. Shangkun Weng, he was my former PhD student. Right now is a professor in Wuhan University. And Hongwei Yuan, who just recently graduated PhD working in Macau, University of Macau. So the things I will discuss on smooth transonic flows. So that means there's no shocks, no contact discontinuities, as Delpha mentioned. I try to concentrate just on the smooth part of the solution. Okay, so the main issue, the key issue I want to emphasize, I want to get conditions. I can get smooth solutions. Okay, avoid to have all the singularities as much as I can. So I will give you an introduction, which Delpha already gave to you, but I will from slightly different point of view, and why this guy has mixed type PDEs. And then my talk will be on the, mainly on the de Laval nozzle. It's kind of convergent divergent nozzle. And this is because this is a problem when 30 years ago I was a postdoc in Crunch, and I went to discuss with Catherine Moravitz. That's a problem she gave it to me. And I haven't been able to solve them, but to keep the problem so far. So that's, I will tell you some progress I make on sort of Meyer type transonic flow in de Laval nozzle. Meyer type means it's actually physical, the only kind of transonic flow which you might expect to be smooth. Because the nozzle flow, as Delpha discussed, could be very complicated. You could have discontinuities and very complicated patterns. So to have a smooth solution, in fact, is you have to be quite special. And I will tell you, and indeed we can, in some cases, we can get a kind of smooth solutions called a Meyer type transonic flow. And so that's a problem given to me by Catherine Moravitz when I was just went to Crunch. And then I will discuss something different from the nozzle flows. It's called a spiral it's a kind of flow turning, and to get a spiral type flow, and which could be transonic also. And even though they are all transonic flows, but their structure, as you will see, the degeneracy, the change type have different geometry, different properties. Therefore, they require different techniques. And then, in contrast to a previous talk, my talk will be more on the flows with vorticity and also the flows with acceleration. Okay, I will tell you why. And the last, if I have time, we will discuss some recent work I did with Shangkun Wang on three-dimensional because most of the talks you heard before is on two-dimensional, where you have a vorticity formulation. The problem could have a slightly simpler geometry, so a little bit easier to get to the solution. But in three-dimensional case, the geometry part really didn't help you much. You really need a very PDE type approach. We use some sort of small piece of result on three-dimensional smooth flows. So the equations already written by Hua in the previous talk, but I'm starting with a very simple situation that the airplane is already steady. So you don't have time dependence. The compressible Euler equation simply is a continuity equation, momentum balance, and the energy conservation. And I will put an additional force term because the geometry part, sometimes I just keep as a forcing term as a geometry to get some sort of patterns. So this phi is a given potential of external force. I will discuss, sometimes take this to be zero, just pure Euler equation. Sometimes I do discuss to see the effects of this external forcing. But anyway, so this is a standard steady compressible Euler equation, continuity equation, momentum balance, and energy conservation. Okay, so I use the same terminology. The pressure is a function of entropy, and it's a polytropic density. So this S is the entropy, and the capital E is the total energy, the internal energy plus the kinetic energy. Phi is the potential of the external force. And in my discussion, there will be a very, here I should add a phi there also. The Bernoulli function will be very important in the discussion, okay? So there should be, in the case of phi equals 0, this is the Bernoulli function, but if you have a phi, you have to put a phi here also. And there is a number, dimensionless quantity called Mach number. Mach number is defined to be the ratio of the speed of the fluids over the local sound speed. Local sound is given by this. You given the pressure equilibrium states, and you compute the local sound speed. It's just given by, you differentiate the pressure with density, take a square root. Okay, that's a local sound speed. So this Mach number is defined to be the ratio of your real fluid speed over the local sound speed. This is a very important quantity in fluid mechanics. The Mach number is dimensionless, and all you heard about transonic flow, subsonic flow, all depends on this Mach number bigger than 1 or less than 1. Less than 1 we call subsonic flow, bigger than 1 we call supersonic flow. M equal to 1, sonic. Okay? So this kind of equation, as the Hua already discussed, even in 2D, if you don't assume it's irrotational, then the equation is very complicated. Even in subsonic flow. Subsonic people think it's very close to elliptic, but actually it's not elliptic. Why? Because even in 2D, you can find this is the first order system. You compute the Jacobian, you find the characteristic polynomial has 3 roots. Okay? Y is always hyperbolic with corresponding particle path. It's always real. However, there are 2 characteristic speed depends on which determine the sound waves. It's given by this guy. You say this is speed square. This is local sound speed. So if Mach number bigger than 1, this guy is positive. Then you have 3 real eigenvalues. That means you are really hyperbolic equation. But if it's subsonic, this is negative. Then you have a complex conjugate. So that means your speed of fluids become complex. So these are elliptical modes. So therefore, in the subsonic region, our Euler equation, even in 2D case, is not really elliptic equation as people expected for the irrotational flow. It is elliptic hyperbolic already. Even you say, how do I care? You cared because this kind of hyperbolic coupled with elliptic makes things very different. How do you give boundary conditions? What kind of boundary condition you have a well-posed problem? It's not a priori clear. Also, as Professor Hua Wang discussed, the two-dimensional result he was talking about, even for the contact discontinuity, if you are in a three-dimensional case, you don't have the vorticity formulation, then you will say even in a subsonic region, to get a prior estimate becomes extremely difficult because the coupling of hyperbolic modes with elliptical modes makes sense even in the subsonic region estimate becomes extremely difficult. Okay, that's one of the difficulty why to generalize those kind of results to 3D. And the important thing is the sonic. If the flow have a sonic, then the equation becomes degenerate. Okay, and from the supersonic part, it's become your characteristic space dimension will reduce, and the strict harmonicity become equal sum. And your original diagonal matrices becomes Jordan block forms, which give you a lot of technical difficulties. If you look from a subsonic sonic side, then the equation on the sonic stick become parabolic. So this kind of very, very difficult situation. So for smooth flow, just like you have airplane, if you started with all of the subsonic, then you speed up, you accelerate, then you will reach sonic states at some stage. Then past that, you become supersonic. Then there's no way you can skip the sonic state. There ways you skip it is you through discontinuity, like contact discontinuity or shock. Otherwise, there's no way you can skip this degeneracy. That's why even smooth transonic flow is a difficult problem because you have this degeneracy in it. You have to overcome this kind of difficulty. Okay, so since this change type, since the degeneracy, so if a flow contains both subsonic, supersonic, and sonic region, the degeneracy, as Dehua discussed, is completely open. Okay, there's no very good general systematic theory for mixed type equations, in particular for the steady compressible Euler equations. It's not clear. But there are many, many interesting transonic flow patterns, and which, as Dehua discussed in his theory. And so the question is, can we study this so-called physical or geometrically interesting flow pattern, which give us some hints how do we expect a general theory? Okay, so let me give you some examples. In particular, the example I want to work on, which is the famous called Courant-Friedrichs problem. The problem is quite simple. You look at steady flow. You have a de Laval laws, which means you convergent, divergent. Assuming you have an incoming flow, which is subsonic. You think everything is smooth, the flow is convergent. But Bernoulli tells you if you have a convergent nozzle, the speed of flow will speed up. Okay? From subsonic, somewhere if there's no discontinuity, somewhere you will reach sonic states. The question is, where do you reach the sonic states? The experimental state tells you, if you near the throat, the lateralist part of the nozzle, the solution is still smooth. Then nearby you will reach sonic somewhere here. Pass through that, then you will come to the expansion part. If the flow here becomes supersonic, then in the divergent part of the nozzle, supersonic becomes more supersonic. There's no shock wave, nothing will appear. And then the flow will flow out. You will get a smooth transonic flow from subsonic, sonic to supersonic. That's called a Meyer type flow. But in the engineering design, people want to design the geometry of the nozzle, design given the Mach numbers of the incoming flow, they want to reach a very high exit pressure. The end pressure is prescribed to be very big. That's what we want to achieve. But if you want to achieve that, the flow coming from here, you see, this is the divergent part. Flow is supersonic, become more supersonic. By Bernoulli, no, the density will become less. Then the speed will become less. Okay, and then the pressure will become small. So the pressure cannot reach the given pressure states. Then the engineer will know, well, they can throw a shock. It's called a transonic shock. The flow will jump through a shock from a supersonic flow to a subsonic flow. And the position of this shock, which is the linear free boundary, will depend, the geometry depends on the incoming flow, and that depends the range of the given exit pressure. Okay? So this is actually called current Friedrich transonic shock problem. It's in their famous book. And in special cases, you can find the solutions. But in general, this is an open theory, whether you can establish such. Actually, in their book, this is a three-dimensional thing. Okay, I draw on a two-dimensional picture for you. But this phenomena could be true for two-dimensional asymmetric flow, also three-dimensional flows. And the problem for three-dimensional flow is completely open. Okay, this problem more or less solved for the two-dimensional case. Okay, but let me forget about these shocks. Just concentrate on this smooth transonic flow, which is the flow given here. Okay, it's a convergent, nozzle, divergent, and the subsonic flow coming in, and somewhere becomes sonic, and it becomes the red part being supersonic. The question, this is a problem was given to me by Moravitz when I came to Quran. Can you prove, actually, some of her previous student, PhD student, wrote a thesis, get some partial result. Can you prove the existence? What is the right boundary condition you can put on? And can you obtain a smooth Meyer type solution for this one, okay? And because experimentally, this is a very typical smooth transonic flow. Another flow is corresponding to the what is called the flow nearby the airfoil. You have a supersonic bubble. And that flow, if it's smooth, it has to be unstable by Moravitz. So it must contain shocks. Then the problem becomes much more complicated. So I will keep my talk will mostly concentrate on this kind of flow. Okay? The flow from subsonic to sonic and supersonic. Can you prove the existence of such kind of solution? Okay. Now I want to do for three-dimensional case. Because in asymmetric case, you can prove some theory as I will discuss. But then it's more like a two-dimensional case. Things become slightly easier because two-dimensional case, there's always a nice thing with string function. If you use string function, you can simplify the geometry, and also the big advantage is you can improve the regularity in the subsonic part, and which is why you have a hope to do a two-dimensional. But in three-dimensional case, the string function doesn't help you. String function is still a vector. It's as complicated as before. Yeah. Yes, smooth transition. So therefore, where is the sonic is the most difficult part. Yeah, because that's where you might lose the regularity. You change type. Okay, you have a topological singularity. Yes, you say what I'm concentrating on is I take this part away. I forget about the shock wave. Okay, my concentration is just on the smooth flow part. Okay, because this already give us a lot of headache, as you will see. Yes, I will do this. Well, we didn't solve the three-dimensional fully, but we have some three-dimensional result also. That's what I want to present. Yeah. Yeah. Oh, okay. I will discuss with you. Yeah. Okay. So this is one type of the transonic flow. The transonic flow actually was found by Curran Friedrich himself. Then by using the in two-dimensional case, you can use the Hongwei transformation. They found using Lagrange transform, they found particular solutions, which is, for example, you're starting from you have a cylinder inside, okay? Then you have another cylinder outside. And then you're starting for a supersonic flow, and then you turn it around, get out, and then you find that there's somewhere a line. On that line, it becomes sonic, and the flow come out, going throughout the external cylinder. They found this solution by using the Hongwei transformation, linearize the equation, and then they found the solution by hand. Okay, and similarly, you can accept a limiting circle. You can also therefore spiral in, turn in, and then from subsonic flow turn in, become sonic, and become supersonic. Both kind of flow this. And we want to say whether this kind of spiraling flow is stable, in structure stable. We don't know how to do the dynamical stability, but we try to say whether it is so we can get some structure stability. Is this kind of flow can be perturbed? You still have such a similar structure. This flow will be very different, as we will discuss, okay? The degeneracy completely different in the following sense. The most famous change of type equation where everybody studied PDE will know was the Tricomi type equation, Kurdish type equation, and the Lorentz-Vitesse equation. So the Tricomi equation, which the Hua also mentioned before, this kind of is, you say, when y is positive, this is elliptic. When y is negative, this is a wave equation. When y equals 0, it becomes degenerate, right? This y equals 0 is a sonic line, it's given. If you compute the characteristics, you find y equals 0 is 9 characteristics sonic curve. In other words, on this line, there's no characteristics grow out. Okay? This is a typical called the Tricomi type equation, which started by Tricomi, and later on was started by many people. But let me say, even for the linear theory I will discuss, even for the linear well-posed theory, this was not completely solved. Because the question is, how do you study boundary conditions for such an equation? It itself is a very complicated. There's another equation. So you change this y to here. Okay? Then you say y equal positive is elliptic. Y is negative is hyperbolic. Y equals 0 degenerate. This way you say the y equals 0 is still sonic line. But then this sonic line it itself is a characteristics. Y equals 0. So there are characteristics which has degeneracy here. So this is called a Kurdish type equation. Yes, as you say, if you, the previous flow, for example, this kind of flow, if you linearize, but if the Euler equation, you linear around this kind of flow, the typical, sorry? No. Even for the nonlinear equation, if you do the, in a two-dimensional case, you do the holograph transformation, you can find the pressure such this is achieved. That's why the Tricomi gas, they think this for special equation of states you can achieve this. Yeah. Yes, that's also after holograph transformation. That's right. Yeah. Very nonlinear. That doesn't work for high dimensions. Doesn't work more than 2 equations. You are right. Yeah. Good. And that's the what that's discussed. You missed it. Yeah. That is another motivation. But quantum pair equation, just as what the discussed on the asymmetric embedding problem, you have similar problems, but their type also can be classified also. Okay. So this Lorentz-Vitesse equation, you don't have the continuous coefficients. You just have a sign change of this guy. So therefore, y positive have elliptic, y negative. This equation has through a jump. The y equals 0 is a jump line. So this corresponds to a linearized equation of either short waves or contact discontinuity. So so this is the 3 type of linear equations, mixed type, change type equations, and this has been studied by many people. But say, for example, there are many people. In the Chinese group, actually among the first group, they study how do you study the well-posedness theory for such kind of equation, Tricomi equation, this type of equation, and including Wu Xinmu, Ding Xiaxi, and Hua Luogen, all the people, they were they were among the group. But the most well-known theory for the community is Friedrichs. Okay, in Friedrichs in 1958, Friedrich said, well, to classify equation hyperbolic, elliptic, parabolic is very difficult. And let's define so-called positive operators, which given boundary condition, we will define operator positive, which combine both equation and boundary conditions when you can find a vector field such that the system with the boundary condition would meet L2 estimate. If you do that, it's called positive operator. Otherwise, not. This turns out to be a very, very important. You get L2 general solutions, and also becomes the whole. For example, in Changshou Lin's work on the asymmetric embedding was based on such a theory, and then doing Nash-Moss iteration, you get a local solution. But that one advantage is you can choose your boundary condition almost arbitrarily because there's a local asymmetric embedding. So the boundary condition he chose to make sure the Monod-Ampere equation is now called bilinearized, and then doing Nash-Moss, you improve the regularity, even though you lose regularity, but you get the solutions. I will do so that's why fluids, you have to do the right physical boundary condition. Not you cannot do the arbitrary one. That's the main thing I will discuss here. Okay, our fluid people is different from you. We want to consider problems which have physical boundary conditions, which can be experimentally observable or realized. No, we can do 3-dimensional also, but not the most. Well, I don't claim that. Okay, just give me a time. I move a little bit on. Okay. Anyway, so there's a lot of studies for linear theory. He also discussed 3-dimension also. But his talk is on 3-dimension asymmetric embedding, right? Okay. Okay. Well, okay, I have to start that. Okay. No. These are the general dimensions. But the earlier result of Chinese group, they're only on the 2-dimension case. Okay. But the Friedrich is more general, just for any dimension, the linear equation, and then you try to find what is the right boundary condition. Then you can find the vector field, and you can get the L2 energy estimate. And then this is a very, very general. And later on, with this idea was using in numerical analysis, possible scheme, everything in this case. Okay. So, but later on, this theory was improved by mainly the Russian group. Okay, this at least they could be high order equations, also high space dimensions, and different types. They try to identify suitable boundary conditions that you can get this Friedrich theory generalized. The Russian group has done many things. The American group, in America, there's mainly the people around Moravitz. They have, for example, this Moravitz group, and I think this was the postdoctor of Moravitz, and they will study the trigonometry problem, trigonometry type equation, could be high dimension also. But they study Dirichlet boundary conditions. That means you only assign the Dirichlet boundary conditions. Yes, the Russian group actually done many good things here also. Yes, but the Moravitz group, I will tell you, the Moravitz group actually has something nice, is that they find for weak solution, even with Dirichlet boundary condition, if it is trigonometry type, then they find a weak solution, always exists, but they don't know how to improve the regularity. They don't have uniqueness. Then they find they have uniqueness, but they they cannot find the existence. Then eventually they find one class of H1 solution for a PDE which is trigonometry type with Dirichlet boundary condition. You have both existence and unique. But unfortunately, they cannot apply the same theory to the high order derivative estimate. The H1 is the utmost they can do. So this was they were started beginning at 2.7, and later on they even give a variational characterization of such a linear theory. And this result was later on was generalized by Otway to Kurdish type equation, also with the differential multiplication. They can get an H1 solution, but not high regularity. To get high regularity, that's the main input we are going to discuss later. Okay. Our theory also depends on the linear theory, but we want to do a theory at least in H4. And that's the difficulty we are facing. And okay, just comments to Professor Yang. You are right, the Russian guy actually later on, they did something even for linear problems, which is mainly Kusumi. Kusumi actually, they did a smooth transonic flow for Wang equation. It's not the potential equation. He cannot do potential equation, but he do what's called the small disturbance equation. It's much more simplified potential equation. And they did it for a rectangle. They found a smooth transonic flow. But the book, they really generalized this Friedrich theory in a very nice way. Give constructions of solutions by colloquial method, give a framework. How do you try to look for vector fields? You can get adjacent out. So it's this guy's book actually is quite nice. And Moravitz, of course, is a big person in this theory. And as Dehua mentioned, she has many publications. In particular, 204 paper, Dehua just mentioned. She gave a survey. The title of the paper was Mixed Type Equations with Application to Transonic Flows. In that paper, he outlined the convection and convergence theory and studied how do you try to study the mixed type equations, whether you have a linear or nonlinear theory, and solve the problems. So it's a very nice paper. But her this guy, yeah? Do you know that? I know. We never know this guy has a problem on this one, yeah. I see. Okay. We never know this guy has. Okay, we try, we find out. But yeah, I know she's a great mathematician, but I never know she did something out here. Okay, we will find out, yeah. So anyway, Moravitz, I think the main, most important observation is that for the airfoil problem, the smooth transonic flow, which with the supersonic bubble, which Dehua just showed in the picture, is impossible. The supersonic bubble, the free boundary must be a combination of whatever conjecture. It's a sonic curve combined with a shock. And everywhere else, it is subsonic. In the supersonic bubble, it's a free surface, which consists of a sonic curve and part of it is this is a conjecture made after Moravitz, because Moravitz showed if you have such a smooth teletype transonic flow, then either it doesn't exist, or if you exist, you perturb the supersonic region slightly, it will go away. So she wrote a series of papers, and which actually make Lippmann Beers and Friedrichs have a long discussion published in the Proceedings of American National Science. This what happens even for a subsonic air flight, and the air wind has to change shape. That's why the conclusion is there must be a shock, even though the airplane flying with a Mach number less than 8, the 0.8. So it's a subsonic flight, but you have a big change of pressure, okay? And so due to Moravitz's work, so Friedrich's solution to the problem he discussed, this supersonic bubble problem, the boundary is not a smooth sonic curve. Part of it must be a shock. That's all. But that's why a problem is still unsolved because the free boundary, one part is degenerate, one part is the shock. Is completely nonlinear free boundary and they have a peak matching together. So this is the conjecture is completely unsolved. And then there's another geometric analysis has mixed chain type equation. Doha give a very complete survey. So I'm not an expert, so I will skip this part, okay? And also the nonlinear theory, Doha also mentioned, Gerbach, Schieffelmann, Beers in the 1950s. They also studied this, but their theory is merely on subsonic flows and rotational. So therefore, it is a purely elliptical equation. But they do have a problem. They also deal with the subsonic sonic. If you have a sonic, then where you will reach a sonic. But they have to assume the flow at least C3 smooth, try to see where the sonic line is. But the existence of such a smooth flow, only 2D, only 2D. But the question is, you don't have existence of such a, because you have a degeneracy, you don't have such a smoothness. Okay, so they have a way to say where is the sonic state, but they assume the flows has to be very smooth. This are realistic, given the degeneracy. And I think that the first linear work, which is complete with more or less general approach, is given by Kusumi's book. In this book, actually, I didn't give you the whole picture. Maybe Professor Yuan was right. He actually gave a systematic survey of what the Russian did. Okay, the Russian did a lot of things on this kind of problem equations. Okay. So here is on the linear problem, I will give you some summarize, okay? So the location of sonic point for smooth sonic flow, as I said, by Gerbach, but only for two-dimensional case. However, there is existence of subsonic sonic flow by compensated compactness, as Dehua mentioned. Could be on the nozzle flow and also could be on the airfoil flow, and which mainly due to the work of Dehua's I think it was study 2.7, and which did later on generalize to the version of many different cases. But this one, this is nice with the compensating compactness, but the solution is R infinity component work. You don't know where the sonic state is. You know the flow is subsonic sonic, but you don't know where the sonic. In other words, you don't know where the speed reached maximum. Okay, you know somewhere it's close to maximum as much as possible, but you don't know where it is. Because solution is only R infinity. There's no regularity. Okay, that's why I started to work with Chunpeng Wang. In a series of work, we try to study, even for the subsonic sonic rotational, means you have degeneracy, all those things. Do you have a continuous flow? Where is the sonic states? Okay, we started to case the sonic state could be a free boundary, could be the lateral is a part of the nozzle. So in a series of work, we try to identify these things. Even study you have a nozzle, the flow shoot out. The boundary is a sonic. So the free boundary is a sonic. Okay, we try to study the rigidity of this sonic boundary. Okay, and the nozzle somewhere becomes flat. The free boundary becomes flat. Okay, so it's called the rigidity problem. This actually was first studied by the Chepnij, the Russian guy. They were first observed the rigidity of the sonic jet problem, and we were able to generalize that to the general cases. If you forget about the subsonic, you look at the sonic, supersonic flows, and then we can prove if the nozzle geometry is expanding, even in 2D or 3D, then you can get smooth flows. Okay, and I will. But most of the work is on 2D, as Professor, or at least symmetrical flows. But the real 3D is quite difficult. And the work we really enjoy is that Chunpeng Wang and we in a series of work we prove indeed this flow exists. The Meyer type of flow exists. However, we have to assume this nozzle at the throat is very flat. How flat? A flat is almost, this flat comes, assuming this part converts x to 0, the graph here has to be bigger than x to 4. Okay, so it's very flat. Then we can prove the sonic line is just across this throat. Then on the left, it's subsonic, and it becomes sonic, and it becomes supersonic. So with this one actually is the first result with physical boundary conditions. We can get this Meyer type smooth transonic flow. Okay, with sonic at the free boundary. Okay, and recently we were able to get the sonic actually on not on the just on the line, on the whole piece, and then the flow becomes supersonic. Okay, and then I will skip the shock with shock. There are many words with this one. Then there recently there's a work by Weng, the former student of Feldman, and they were able to, if you put the Euler-Poisson equation, then Poisson gives you an external field. By changing this field, then you can get a smooth transonic flow for the steady Euler-Poisson. But unfortunately, their method only works in 2D. It doesn't work for the 3D. So in my talk, I will focus on the smooth transonic flow, for which the main difficulty will be the Euler equation are mixed hyperbolic, even in the subsonic region, and the change time from subsonic to supersonic. The main difficulty is, as what the professor asked, can you identify suitable boundary condition? It's not artificial, which depends on the solution, which are extremely different in general. Okay, we want to the boundary condition is physical, means you can really realize this guy in the lab. Okay, and the degeneracy of the Euler equation at the sonic curve depends on the geometry of the nozzle, depends on the, for example, if you have a nozzle, depends on how narrow is the nozzle. Okay, and on the location of the structure of the sonic curve, which are not known in domains in general. And another important thing, we don't want just deal with potential flow. We want to deal with fluids which has vorticity, because potential flow is only a mathematician's toy model. In the real fluids, it must have vorticity. But if you have vorticity, then in general, you will lose derivatives. The question, then how do you get a high H4 theory? Becomes extremely difficult. Okay, how can you gain regularity in the transonic region? Becomes really difficult. Okay, that's something we want to discuss. Of course, you know that Professor Beers was the first person to try to start the real nonlinear problem. But then he found that you have to, and you really have to understand the structure of the sonic curve very well to do. So he had developed a local theory. This was later on by a Chinese group, Hong Jiaxin. They will pick this up. They are assuming that you have a subsonic flow, well, potential flow. So there's no vorticity. Assuming that you were able to solve the elliptic equation, you get a subsonic flow, and the subsonic flow approach on the smooth curve S becomes sonic. The question is, can I extend the solution to the right to get a supersonic flow? So they call this called a supersonic bubble problem. Then he found, well, you cannot always do that. The only way you can do it is this sonic curve must be non-exceptional. What do you mean by exceptional? Exceptional means if you have this curve, sonic curve is given, they have a normal. This is your flow direction. Then you study this. If these two guys coincide, then it's called, this flow is exceptional. If it's not coincide, they are non-exceptional. Then they were able to prove that this introduce the concept of exceptional point. They proved the following fact. If the point on the sonic curve is non-exceptional, then there are always two characteristics from the sonic curve grow to the supersonic region. In this case, a local existence of supersonic equation is possible. So therefore, you can extend the subsonic flow to supersonic flow. However, this is singular in the sense that the local supersonic extension is impossible in general. Okay? Indeed, this characteristic, there's no characteristics in the supersonic region from the sonic point, which is the interior of these excitation points. Okay? So if we have a set of the excitation points in the interior, there's no characteristic grow out to the supersonic. In this case, you can prove there is no unique extension. So therefore, this tells you the sonic curve, the structure is very important. Otherwise, if we don't have a local, this has no boundary, just a local extension from subsonic to supersonic, smooth transition, where that is possible. Okay? So therefore, then Chunpeng Wang, we try to study the excitation points. Actually, we have a quite a clear description of the set of this so-called sonic point. Give a structure of this thing. But it turns out this is not that crucial in our little theory. Okay? So now let me tell you a little bit. The first result we did is on the smooth irrotational transonic flow of Meyer type. So that's our first result, is two-dimensional and irrotational. The nozzle is convergent, the de Laval nozzle, convergent divergent. So what I expect is we want to give a physical boundary condition. The flow coming in, and this wall is solid, so flow cannot move out. And because it's convergent, somewhere becomes sonic, and then becomes supersonic, then come out. The question, this is a physical boundary condition, with a physical boundary, this one, you also have to specify the boundary condition, so that you can achieve this. Well, this, for simplicity, we assume the nozzle is symmetrical, it doesn't matter, okay? So you only have to study the upper one. And then our theorem is the following. Assuming that the boundary is smooth enough, okay? The left is 3 alpha, and the right is C4, and the incoming G is C3 alpha. Then we can prove if the nozzle is suitably flat in its throat, in the following sense. Near the throat, it's a constant plus x power, which power is bigger than 4. Eventually, we can prove, this is almost necessary condition if you want to have a smooth transition. The sonic is. Now, if the nozzle is short, we can prove, we can prove a very strong solution. Even though we have degeneracy, it's a C11 smooth solution. The transonic of Meyer type, it means it becomes subsonic, sonic, and then supersonic. The regularity is C11. Okay? And this actually has something to do with what the Professor Yuan, for unimperial equation, in the degenerate case, you also obtain a C11 solution. Here you also obtain a C11 solution here also. But we only get a solution which is the nozzle is quite short. And so the question is, can you extend this small thing to global? And then it turns out the supersonic extension becomes very simple. And Chunpeng Wang and we studied it earlier. We said if you have a sonic line which is straight, just at the throat, then this becomes expansion. Then we can prove the flow becomes really smooth, no shocks, nothing happens. But if this guy grows very fast, there is a Kongqiang. There develop a free boundary inside between the wall and here, no gas at all. And the solution is changing smoothly. So this is a physical vacuum. It doesn't have nothing to do with the physical vacuum typing new or this studying this solution has to be. Now, this is very smooth. And when we found this out, I discussed with people in doing this Fengdong, the wind tunnel. They observed this a long time ago. But this is the first proof that you can find a vacuum region automatically from expanding nozzle by supersonic flow. Okay? So therefore, the extension to supersonic part is quite easy. But turns out that the most difficult part actually is on the subsonic extension. We thought, subsonic equation become elliptic for rotational flow. It should be much easier. But no. Then we found actually the subsonic extension is not always possible. it depends on local structure of the nozzle wall, it is the throat, and the height of the nozzle. For given geometry, it is throat, we can prove there is a critical H star. If such that the extension is possible, if only if H less than equal. Otherwise, you could have sonic states on both on the physical boundary and also on the throat. That was very surprising to us that the sonic state, the maximum principle, the sonic can achieve both on the physical boundary and in the interior, not just on the. So this was surprising. But anyway, so at least we can find one class, we have a global solution for Maya type. Then you might ask, what is your boundary condition you put here? And here, it's not this is the physical boundary condition because no flow in, flow out. Here, we just give flow angle and the mass flux. So the physical boundary condition, we can solve this problem. Here is on the x is hyperbolic. We do not have to specify any boundary condition. The problem becomes well posed. Okay, so this in this theorem, the set of sonic points is a line, but the good thing, so we can identify where the sonic line. The better thing is also that. Better thing is we need this very flat, which is almost necessary for this sonic line growth on the slot. The question, if this guy, let's say this power is to 2, just convex, then what is the sonic line? That's become a mean open problem. Do you, in this example, in experiments, if this, in general, if this nozzle only here is not that flat, the sonic line is a real free boundary. It's not just on the throat. It could be just slightly away from the throat. The question is, can you do that? But our case, we cannot do it. Okay, this theory didn't tell you anything about that. Another problem is the boundary, the sonic line is characteristically degenerate. So therefore, the linearized equation is Kurdish type. It's not Pickerman type equation. Okay, there are Pickerman type problems. How do you do that? Okay, so it's not clear from this theorem. That's why we want to do the other cases. Okay. So this is a kind of in the theorem. The set of sonic point is a line in the throat, which is characteristic degenerate boundary in the subsonic region. While in the supersonic region, all characteristics from the sonic point coincide with the sonic line, and never reach the supersonic region. So all the sonic points are exceptional. That's very surprising because this is just opposite to what Beers proposed. We found the sonic line, every point is exceptional, but still you can do the hyperbolic extension. So that's very surprising to us because at the beginning we thought this seems completely opposite to. I think the reason is we have a physical boundary condition, and in the discussion of Beers, there's not. Yet the geometry of the sonic curve in this case is simple, okay, which is a crucial in our analysis. We have this straight line. The geometry can trivialize. This is so therefore the shape of the nozzle could be quite general. Yet the assumption of the suitable flatness is almost necessary. The flattening implies the sonic curve becomes a line throat, and the transonic flow has 0. So this is the whole point. The transonic flow has 0 acceleration at the throat, which is physically not very interesting because physical next the airplane take off, you have to accelerate from subsonic to sonic to supersonic. But in our case, you can prove the acceleration of your actually the sonic become very flat. There's no acceleration. The acceleration actually is 0. So this is something is not satisfactory. But anyway, this is the first existing result on smooth Maya type rotational transonic. In general, also with the physical boundary condition. Okay. So in the case of nozzle is not flat, super flat. The geometry of sonic curve is much more complicated, and there will be truly free boundary analysis. So our analysis cannot be easy to apply. This is the open problem, whether there exists smooth transonic flows with 9 flat sonic curve and the non-zero acceleration, which could be irrational or with vorticity. So this is the main thing we want to address. Another problem is that our theory with Chunpeng Wang is really a two-dimensional theory. And the reason is that all our prior estimate depends on the Chapelian equation, which has a potential and the stream function as the independent variable. But this is impossible in high dimensions. In high dimension, potential still could be, but stream line with a vector, okay? So it cannot work. So this approach depends too much on two-dimensional. And if you want to do any high dimension of analysis, didn't give you any help. And that's why we want to develop something that a lot depends on Chapelian type equation. And we still want to study transonic flow. So that's something we want. So the first example we try is the spiral transonic flow. And in this case, the sonic curve is not exceptional. And also that you have accelerations. And the first spiral flow, as I showed to you before, was did for the rotational flow by holograph transformation. Using the speed and the flow angle as the independent variable. You change the rho. And this phi is a Lagrange transform of the velocity potential. Okay? And if you write down this equation, this is the linear equation, you can write down purely circular flow, just given by this. Or you can write down purely expanding radical flow. You do a linear equation, you do a superposition, this will give you a spiral flow. This is the exactly give you some, you check this, this give you the examples I gave it to you, this give you the spiral flows. However, this kind of approach, for people like mathematicians like us, this doesn't make too much sense because not so many equations you can do the hologram transformation. Second, this hologram transformation, you get a solution, but going back to physical space, in general, does not match with any boundary conditions. Okay, the hologram transformation, because they change the roles between dependent and independent variable. You're going back to the physical, it doesn't give you any, doesn't make sense too much for the physical flaws. Therefore, we look at the problem from PDE point of view. And then actually this spiral flow came by look at this ODE system with specific boundary conditions. You can study the flow spiraling out from inside, or you can study the other way, you spiral in, by studying this ODE system. And if you do this carefully, indeed, you can prove there are pure supersonic flows. There are also pure subsonic flows. But there are cases which you have both transonic flows, smooth transonic flows. Okay? And so therefore, we take the flow which going from outside coming in as sort of background flow. We try to see the PDE formulation, how this solution will be structurally stable. Okay? And so we call this as the background transonic spiral flow. And then we try to study the structural stability of the transonic spiral flow. So we denote the background flow by B, okay? The question, how about the structural stability of transonic flow? At the beginning, we only studied the two special kind of perturbations. The main thing is, what are the boundary conditions? What Professor Yao just asked, which is not artificial, but physical makes sense, okay? So we only study kinds of perturbation of this sense. We write down the Euler equation, steady Euler equation without a force, this type of, without external force, purely Euler equation, in the cylindrical coordinates, okay? It's very difficult to start the general structure and the generic three-dimensional perturbation. So therefore, we started with two classes of support. One is the stability analysis and the perturbation independent of symmetry axis. So this means stability and the cylindrical symmetrical perturbation. Another one is stability under the symmetrical. But later on, we can say we can do the general three-dimensional case also. And if for the case which only symmetrical perturbation, okay, then our problem becomes simpler. This A is corresponding to entropy, okay? So then this becomes our PDE. Here is a boundary condition. So to answer Professor Yau's question, we give boundary condition. As an entrance, we give it the Bernoulli function. We also give it the entropy. However, we give it a relation between the velocity and the entrance. Okay? So, A and B, which only moves with particle paths. So therefore, it's a hyperbolic equation, so given the initial data, which is okay. Okay? So this is R1. But for the R0, this guy is what? This is a flow angle restriction. You see, this is a relation between the two components of the velocity. One is the angular, one is the radial direction. This tells you there is a restriction on the flow angle, the flow in which we come in. So this is a physically acceptable boundary condition. This one is out on the exit. Okay? So the Bernoulli function and the entropy are conserved on a particle path, so therefore it's natural to give in their boundary condition and the entrance. The condition 7-8 represents is restricted on the flow angles at the entrance and exit, which are all physically acceptable and experimentally controllable. Okay? And so this condition 7-8 turns out is admissible. In fact, we can prove mathematically this condition is the right condition. We can find a priori estimate to close our argument. So using the standard Sobolev norms of those things, we can prove the following theorem. And for the physical gamma between 1 and 3, and later the background flow, which indeed has the radial velocity expanding. Okay? And this is the condition on the Mach number, but actually this is not important. Then indeed, as long as the boundary term has such a regularity, but look, the velocity sense is h3, but the hyperbolic moment is higher regularity. Okay, I will tell you in a minute why. Then we can prove that this epsilon, if a perturbation is small, then the problem, this transonic problem with this boundary condition, indeed have a solution. The solution, the velocity is the h3, but the hyperbolic moment is h4. Okay. More than that, this solution is close to our background spiral flow as much as you want, controlled by the initial perturbation. More importantly, we can prove indeed it is a transonic flow in the sense we can find a smooth C1 curve, okay, such that the C1 curve is very close to the sonic line of our background flow in the C1 law, such that the flow on the left of this curve is subsonic, becomes sonic on this curve, and it becomes supersonic on the right of this curve. Okay, so this is this flow control have a non-zero vorticity, and the first result on the existence of non-trivial smooth transonic with zero. Okay, the spiral flow. And also this condition on the Mach number actually is not important. It's on the background, okay? Due to the non-zero angular velocity, the sonic component is all non-exceptional, even for the rotational flow. Okay? So therefore, this the method here is completely different from what Chunpeng and I did for the rotation, for the potential flow case. Okay? So the method is completely different. The actually similar structural stability can be realized, can be obtained for the asymmetrical perturbations. Okay? So let me just say a few words on this analysis with the rotation. We had two parts. Actually, we started with the rotational case. Then the analysis of linearized equation with mixed boundary condition, the choice of the multiplier and the application of the middle boundary condition is a key rule. Okay, so we give boundary condition which is physically reasonable, and this multiplier depends very much our equation is in this case is Kurdish type regularity. Okay, and the construction of solution is Galerkin method. This actually was motivated by the Kusumi's work for Kami equation. Analysis of the sonic curve we just by implicit function theorem. The case with the non-zero vorticity is much more difficult. In that case, we cannot use the standard subsonic sonic decomposition as we did before. What we do is we have used a new formulation which is called the deformation curve deformation, which was developed by Shangkun Wang. We did this for the subsonic flow case, but then we found that this for deformation is very good, give you the optimal regularity. And for this guy, we developed a two-layer iteration to avoid the losing of the derivatives in the transonic region. Okay, and here, why the two-dimensional important? We're still using the streamline function, which improve regularity in the uniform subsonic region to recover the loss of derivative in estimating the first-order derivative mixed type equation. And this is why it doesn't work for three-dimensional. Okay, I will need a new idea in the later on. The real analysis coming, how do you study this linearized Kurdish type equation? This is a boundary condition. For this boundary condition we put on. This is on the entrance, this is on the exit. You see, this is a Robin type boundary condition for the potential. And this is Neumann boundary condition. Okay? And this one is a Dirichlet boundary. So this boundary condition is a kind of mixed type. You have Neumann boundary condition, Dirichlet boundary condition, and Robin boundary condition. We were able to show for this linearized equation, it's actually the Trikami type equation, but we were able to develop H1 estimate in terms of the source term and the boundary terms. And based on this one, the importance is we can improve this one all the way to H4. The key difficulty is how do you improve this for high order derivative? That's a difficult term. In the 3D case, that's much more difficult. Okay, so I will finish for you is want to leave. And so the good thing is now we were able to derive this for three-dimensional. We started with the quasi this kind of nozzle, and later on this already published. So this is our boundary condition we choose, and so then we obtain for the quasi 2D model. We were able to prove the background transonic flow and two-dimensional and the general perturbation is stable. But later on, the most interesting recent work, we can do this for 3D. We will obtain two classes of both rotational 3D transonic solution. We also obtain Biotromy type of flow, which with vorticity. And these are all on the three-dimensional result and with physical boundary condition. And so I think the most important thing is that we were able to obtain compressible Biotromy type equation solution for 3D. Biotromy type equation play a very important role for the rotational, for the incompressible flow in the recent construction of so-called non-unique solution by H1 principle. And for compressible, and this was the first systematic study to obtain the flow. Well, definition of Biotromy flow is the following: is that the flow, the curve is parallel to the velocity itself. That's the definition of Biotromy flow. So we were able to prove the general existence of this kind of Biotromy. They are all transonic. Okay, the idea is we have given potential force. We find one class of one-dimensional transonic flow, and then we perturb this in three-dimensional general perturbation. Then we show the two-dimensional solution like this. So we can obtain both the rotational flow and the Chunpeng flow. Okay, so I don't have time, but the result is already there. This actually generalized a lot of by the problem of Yodovich. Yodovich only gave some specific example of control by Chunpeng flow, but our theorem gave a first systematic work on general 3D compressible flow. Okay. And the proof is itself is still based on linearized equation, but based on the Kirch type equation. How do you do the estimate? The important thing is that we were able to do the high H4 estimate for the linear, but we found a trick. Is we want to do the elliptic hyperbolic problem with Transonic, but we don't know how to do it. We change the problem to elliptic hyperbolic problem. And for this new enlarged equation, we know how to do the problem. Then we shrink them back. We get the original problem. So this seems a technique people never used before. That's why we were able to solve the 3D problem. We do not use the string function anymore. We based everything just on the linearized equation. How do you get a high order derivative estimate? And that one, by this technique, we were able to overcome the losing of derivatives and coming back to the analysis. Okay, anyway, we hope our analysis eventually can settle down this Meyer type transonic flow or general nozzles. Yeah, okay, thank you very much for your attention. Yeah. 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 Ah. Yes. Yes, that's a key assumption. Thank you very much for what I mean by flat. Okay, let's go back. This is very important. You came up with a very important issue that. Let's go back to this. Okay, yeah. So flat is you see at the throat, and your throat here, and F equals to H, right? Then you perturb this H. You see my perturbation is in a power which is higher than first order power. But if my throat, the upper bar is only a convex function, which means just H at most is X squared, right? And but we can prove if we want to have the regularity of my solution, if we want to have a C1 solution, this is almost less than sufficient condition. Almost less than sufficient condition. If you want to get a C1 smooth solution, because it's a high degeneracy. So this is if you have the solution, this must be true. So therefore, but if a physical nozzle time, this one is just convex. Then you just H plus X squared, this kind of thing. Then what happens? So my later on work just try to say, in that case, I get a sonic curve. It's not straight line anymore. It's just a smooth curve. It's a true free boundary. Because in this case, in this flat case, my nose just grew. Exactly at this point is a straight line. But in general case, just C1 smooth curve as I proved later on. If it's not flat, you get a C1 curve out. And so the Meyer type flow, we expect here, the sonic line, original is flat, just a straight line. Now it just could be this one or this one, a smooth transition, which seems more physical. Yeah.